have home deliveries to entice people, but I'm sure, oh, there you go. Yes, here's my coffee as well. So, okay, let's give it a shot. And no matter what, things are going to be recorded for people to join after the fact. And I just want to welcome everybody here. My name is Dimitrios Psaltis. I'm the current chair of the Theoretical Astrophysics program. And because of all the lockdowns and the COVID issues, we decided as the Theoretical Astrophysics program this year to change a little bit our format, have all our talks that are normally very nice and formal and interactive, to try to do the exact same thing online in this format. And we also moved the time a little bit earlier so that we can enable people from across the oceans to come and join us. Because this is the first talk of the semester or the year, I guess, what we usually do is we say a few things about the program and welcome the new members. So I would just like for that to introduce Rosie Johnson, our program project manager, who is going to take it from here and then move it on. So welcome everybody, and let's hope for a wonderful semester of talks.
Hello everyone, thank you very much for joining today. We have a few things we wanted to just introduce as we start out this new and very different semester. And I will start by talking briefly about the TAP initiatives that we started, I believe last December or January. So they're just getting started now. And what these are, if you haven't heard of them, is it's an opportunity for TAP members and across the 3 member departments to get together for informal discussions and talks to discuss research, maybe pursue some collaborative activities. We are developing these around kind of a monthly meeting format with faculty, staff, students, and we encourage anyone that's interested in them to get more information. We have them on the TAP website. There's 4 initiatives that are just getting started now. Some of them are in different phases of development, but the coordinators are listed on the TAP website, and we just encourage you to pursue this additional opportunity to connect and discuss research opportunities with other members, outside of the colloquia, the monthly colloquia. And I don't know how many students we have here today, but we will continue to highlight the Student Research Prize that will be announced later this year. Look for it in December for a, probably, November, December for a January due date. But this is a biennial competition. And the submissions will be due in January. The research prize is $500. And I've listed some of the eligibility criteria here. These will kind of be developed a little bit more updated. So in late fall, we'll have more information available both on the website as well as through the listserv. But we just wanted to make sure everyone kind of had it on their radar so they could see it and perhaps plan for it. And then finally, I'll just overview very briefly. Last year and even before that, we had started really focusing on some opportunities to develop additional computational resources that we would like to see available across the TAP, for members and students and faculty. And we've developed a number of proposals. We haven't hit one yet, so we're still trying to get that successful proposal awarded. At this point, we're looking at some different opportunities. There's several NSF grants that may be a good direction to head. Because we don't have it fully fleshed out at this point, I want to encourage anyone that might be interested in collaborating on that, or talking about some joint research opportunities, to either reach out through the TAP email or the computational initiative, which we hope to see starting in the next few weeks. That might be another opportunity. Or CK Chan has been kind of taking a leadership role on that, so you might reach out to him as well.
That's pretty cool.
Caitlin, do you want to talk about the fall schedule?
Sure. So as hopefully many of you seen on the TAP Colloquium website, we have a very exciting schedule. I'll save the introduction of Emily Litchko, our first speaker, for after we're done. But if you look, you'll see that we have talks basically every other week. from world-leading experts in a variety of topics on theoretical astrophysics, and you'll notice that most of them are coming from Europe or at closest New York. So we have Oliver Gressel, who works on MHD and radiation physics in the context mostly of protoplanetary disks. We have Jens Jasche from Stockholm, who works on topics related to cosmology. Deborah Sayaki from Cambridge, who works on extragalactic astrophysics, studying galaxy formation, doing very large numerical simulations. Zoltan Hyman, the closest, coming from the University of Columbia, and he's, sorry, that should probably be Columbia University. He works on black holes, circumbinary disks, jets, things like that. And finally, Barbara Ercolano, who works on photoevaporation and chemistry of protostellar and protoplanetary disks, coming from the Ludwig Maximilians University in Munich. So it's a very exciting schedule. Again, it's a really unique opportunity, I think, to have people speak with us who otherwise wouldn't be able to. I'll mention that in general, we are hoping to be able to set up individual meetings or group meetings with any of these speakers. We're not sure yet how amenable everybody will be, but if you're particularly interested in meeting with one of these speakers, you can let us know in advance, and we'll do our very best to make sure that we get that set up.
Thanks, Caitlin. Andrew, would you like to talk about students in TAP?
Yeah, sure. So yeah, thanks. We're actually still, as we were just discussing earlier, trying to make sure this list is full, complete, and up to date. So if anyone sees any omissions or people who we forgot that have left already, can again send anyone an email. But yeah, as you can see, even with this list, there are a significant number of grad students that are affiliated in one way or another with the theoretical astrophysics program, and we like to think that it's a bit of a community, and that we can lean on each other and use each other as resources in a variety of ways. Obviously, that's a bit more difficult in the current circumstances, where we don't get to gather before Colloquia and do other things like that. So yeah, I just want to obviously encourage people to to reach out as much as they can in other ways, and then obviously to stay tuned for those initiatives that Rosie discussed as well. So yeah, I think I'll leave it at that so we can get on with the exciting talk today.
All right, Rosie, is there anything else, or shall we just transition to Emily's talk?
Let's go on to Emily's talk.
All right, well, I'll let Emily start screen sharing while I do the introduction. It's a great pleasure to be able to introduce one of our newest postdoc arrivals to TAP. Emily received her PhD in February 2020, the last month before the insanity, from the University of Wisconsin-Madison. And she works on a variety of topics related to astrophysical plasmas, mainly in the context of the solar system. She's working at LPL with Chris Klein. She's also quite an award winner. She's currently holds an NSF AGS postdoctoral fellowship. And as a finishing student, she was awarded the Elizabeth Hirschfelder Award at the University of Wisconsin-Madison. And she also held a NSF while she was there, which is now the same thing as a finalist. So I can't think of a better way to kick off our colloquium series than with one of our own. I'll just note a few new rules in this strange environment. we're going to try to maintain what was, I think, really unique about this colloquium series, which was the fact that it was interactive. And that's going to be a lot harder in this format. What I'd ask is that during the talk, if you have questions, if you can write them or even just say that you have a question in the chat window, and then I'll monitor that. And then maybe periodically I'll try to take a break and then let people ask their questions, or I'll read them off myself, and we'll see how that goes. And then we can have a more extended discussion at the end where people are free to just sort of chime in as they please. But if during the talk, if you could not just interrupt the speaker, but just write something in the chat window to let me know that you have a question, we'll try that to just prevent it from getting out of hand. But I encourage people to try to be, you know, engaged and as interactive as possible. So that we can maintain the sort of small, intimate feel of this very special talk series. So without further ado, I'll turn it over to Emily. Oh, and I'll just, sorry, one other thing. If people want to mute their video, mute themselves and stop their video while she's speaking, just so that we don't overwhelm the bandwidth. I think that's a good idea.
All right, so thanks for having me today. So today I'm going to be talking to you about my thesis work, which I did at the University of Wisconsin with my advisor, Jan Egedal, as I'm sure you're able to tell. So my thesis focused on a heating mechanism called magnetic pumping. So the way the talk is laid out, I'm going to go through some of the open questions that this talk is meant to address, and then go through kind of the basic physical mechanism of how magnetic pumping works. And then after that, I'll get into the bulk of the research. All right. Oops. Okay, so throughout the universe, we observe distributions of electrons and ions with these hot power law tails. Because of the low collisionality in space and astrophysical plasmas, it's not entirely surprising that we would observe these non-Maxwellian distribution functions, but determining the mechanisms that generate these hot power law tails is still an open question, and one that's really at the heart of this talk. Specifically, we focus on the role of heating from magnetic pumping, which is a heating mechanism where energy is transferred from fluctuating magnetic fields to heat the plasma, naturally producing power law distributions. While this heating mechanism should be applicable to a wide range of astrophysical systems, we focus on how magnetic pumping can account for additional heating in space plasmas, specifically in the solar wind. So the successful launch of Parker Solar Probe and now Solar Orbiter, this is a particularly exciting time to be studying the solar wind. These spacecraft are going to allow us to better understand some of the biggest open questions in solar physics, several of which are encapsulated in this graph of temperature as a function of distance from the sun. What is arguably the most famous open question is also the most obvious, the coronal heating problem, where the temperature jumps from about 6,000 degrees Kelvin on the surface of the sun all the way up to over 1,000,000 degrees Kelvin, over the course of a few tens to 100 kilometers, far faster than can be accounted for by diffusion alone. So it's an important part of Parker Solar Probe's science mission to look into this open question, but even past this point, we see a discrepancy between the observed and predicted temperatures. So as plasma streams out from the sun, we expect it to cool adiabatically, but as you can see, this is not what is observed. Understanding the additional heating mechanisms that causes this gap right here is going to be one of the open questions that I'm addressing in this talk. So there's been a lot of work done towards determining the mechanism that provides this additional heating. Most of it is focused either on the turbulent cascade, where energy starts with the large scale fluctuations, travels through the cascade, and is injected in the kinetic scale, or through wave-particle interactions, where energy is injected at a particular resonant velocity. In both these mechanisms, since energy is injected at a particular scale, it makes it difficult to reproduce the power law distributions observed in the solar wind. Magnetic pumping is a mechanism that uses these same magnetic fluctuations to naturally generate power law distributions. So because magnetic pumping is fundamentally a mechanism where energy is transferred from fluctuating magnetic fields to heat the plasma, I'm going to start by talking about how these fluctuating magnetic fields affect the plasma in a uniform flux tube, and then we'll talk about how that translates into magnetic pumping. All right, so we have our uniform flux tube, and because we have a uniform flux tube, we know that the magnetic moment and the action are conserved. So using the conservation of the magnetic moment, we can get that the perpendicular temperature is proportional to the magnetic field. So as the magnetic field increases, we get perpendicular heating. We can get a similar expression from the action if we find an expression for how the length of this uniform flux tube element varies with magnetic field. And we can do that by using the fact that the magnetic flux and the number of particles are conserved. So if the magnetic field increases, we know the area has to decrease so that the flux is conserved. And then the length of this flux tube element has to increase so that the number of particles are conserved. So we end up getting that the length of this flux tube element is proportional to the magnetic field. So the parallel temperature is inversely proportional to the magnetic field in this uniform flux tube element. All right. So given these expressions, we can look at how a changing magnetic field will affect just a uniform Maxwellian distribution in one of these uniform flux tubes. So if we increase the magnetic field, we get exactly as you'd expect, heating in the perpendicular direction, cooling in the parallel direction. We decrease, we get the exact opposite. But when we go back to our initial magnetic fields, we get back our initial distribution function. So there's no net work over the course of this cycle. However, if we start with the same uniform flux tube, same Maxwellian distribution function, we increase the magnetic field as before, so we get heating in the perpendicular, cooling in the parallel. And then in between increasing the magnetic field and decreasing the magnetic fields, we add in some sort of diffusive process, some sort of isotropizing mechanism. So this could be pitch angle scattering, this could be scattering off of fluctuations, this could be thermal streaming, anything that isotropizes the plasma. So I find it helpful to think of a flux tube, a phase-space element at that V parallel equals 0 line. So when the magnetic field increases, you're going to get the shifting upwards. And then when the diffusive process happens, you're going to knock that phase-space element off its initial position. So when we decrease the magnetic field, it's not going to go down as much as went up, and you're going to end up with net heating over the course of the cycle. So this is magnetic pumping. We can repeat this process over and over again. So here we have the distribution function as a function of energy, where this red line is the initial distribution. And you can see that as we repeat the cycle over and over, we get more and more heating. And not only do we get more and more heating, but we get this energy transfer from these lower energy to these higher energy particles. And so this is, you know, a cartoon picture of magnetic pumping. And while it is a cartoon picture, and I'm going to go through this model worked out in a little bit more detail later, there are some key elements that this model really encapsulates that I wanted to point out. Number one is that we get the amount of heating is dependent on the strength of magnetic perturbation. So how much this distribution function is stretched. The amount of heating is dependent on the amount of scattering. So how much these phase-space elements are knocked off the initial position. And the amount of heating is dependent on the number of pumps. And finally, and this is the critical point, the amount of heating per particle is proportional to the particle's initial energy. And so that's going to give us this Fermi process that gives us these power law distributions that we want to see. All right, so this is a cartoon model. So I've worked it out in a little bit more detail for a 1D model. And it turns out it works well for particles moving a lot faster than the wave speed, specifically ions moving a lot faster than the wave speed. But we really wanted this to be applicable to actual, you know, a physical system like the solar wind. So in order to make it applicable, we had to add in some 2D physics to our 1D model. And so the way we did that was by adding in the concept of thermal streaming. So this is a uniform flux tube, but if there was spatial variation along the flux tube, there'd be an area of localized pressure anisotropy that would stream away with the velocity of the particles, isotropizing the plasma a lot faster than just by cooling collisions alone. As we may or may not know, in the solar wind between the sun and the earth, there's on average about particles undergo about 1 collision. So this worked really well for the ions. We're very happy. But we really wanted to apply this to the electrons as well. And so it turns out for the electrons, in order to get these power law distributions, we need to include the full effects of 2D physics. And so that includes the effects of trapped and passing particles. And so this is really the most exciting result of my thesis, because it turns out when we include the effects of trapped and passing particles, we can heat particles moving a lot faster than the wave speed. And the exciting part about this is that that's a regime where, like, heating through the turbulent cascade, these resonant wave particle interactions, they don't apply in this regime. And so this is, yes, the most exciting result of my thesis. And so the talk itself will go through kind of this basic format. So I'm going to start with a 1D go through the 1D plus, and then into this final result, the 2D, which is the one that's recently published. I believe the link is in the abstract. But first, going through kind of the 1D model. So I didn't want to get too deep in the weeds here, but I did want to say kind of what we started with and the assumptions we made. So we started with the kinetic equation. So this is kind of at the heart of all the work that I do. So just, it's a statement of the conservation of the distribution function. And over here, we have the Lorentz pitch angle scattering operator. So we take this equation and we assume just a uniform flux tube. So that means the magnetic moment is conserved, the action is conserved, and then we get the number of particles in flux are conserved. So we take this equation, we change variables, and then we get this guy right here. So here we have distribution function evolving in time. So we have this term, which is actually the one where the heating comes from, because this is the one with the fluctuating magnetic fields. We have the effect of compressional physics, and then we have collisions over here. So we have this equation, we can expand in pitch angle. And so from there, we have two options. We can either take moments using these Legendre polynomials or special functions, find a set of coupled differential equations, solve it numerically in the way that we all know how, or we can make an assumption that the distribution function can be split into the slowly varying and the rapidly varying part. And then we can use, we can approximate kind of what the result is going to be. And the nice thing about this approximation is that it really captures a lot of the physics that's going on. So at the end of the approximation, we get this velocity diffusion equation. And the key thing about this velocity diffusion equation is that this diffusion coefficient is proportional to v squared. And so we're going to get the gain in velocity is proportional to the initial velocity, and that's going to give us this Fermi process, these power law tails. We can also look at G, which is essentially the amount of heating per fluctuation. And so we can see that here we have G as a function of scattering frequency. We can see that when there's no scattering, kind of in that initial case, we have no heating. Similarly, if we have an infinite amount of scattering, it's always a Maxwellian. It's never knocked off that, the phase-space elements are never knocked off their position. And again, we get no heating. And so in between these limits, there's this optimal scattering frequency that is the optimal amount of heating from magnetic pumping. There are a couple other predictions from this approximate model. We're going to get power law distributions, as I said. There's going to be a phase difference between the pressure anisotropy in the magnetic field. And there's also going to be heating that's dependent on the scattering frequency and the amplitude of the magnetic field, which is this delta R term right here. All right, so we have this analytic model. It's great, very happy with it. But we tested it using VPIC, which is the particle and cell code developed at Los Alamos National Labs. So over here on the left, we have the domain of the simulation. It's doubly periodic. We've got two oppositely directed current sheets that don't vary in space, but vary temporally. And so you can see the induced magnetic field at this black point here up the top. So we ran using the simulation domain for a number of different scattering frequencies. And you can see that it agrees well with the predictions of our 1D model. So here you can see that for different scattering frequencies, we get that scattering frequency dependent phase difference between the magnetic field and the pressure anisotropy. And also we get heating that is dependent on the scattering frequency. You can see that in a little bit more detail in these plots here. Here we've got energization as a function of scattering frequency. The black line is the differential equation solution to arbitrary order. The red dashed line is the prediction from that approximate model that I just showed you. And then the blue circles are the results of the VPIC simulations. So we get good agreement between the VPIC simulations, the approximation, and the differential equation solution. Similarly, for the phase difference between pressure anisotropy and the magnetic field as a function of scattering frequency, the black line is the differential equation solution. The red dashed line is the approximate solution, or is the approximation, and the blue circles are the VPIC simulations. So there's good agreement between our 1D model, these PIC simulations. We're very happy, everything's working out. However, we really want to apply this to the solar wind. In the solar wind, the collisionality is very low. And so if we assume this low collisionality in the solar wind, we don't really get that much energization. And so in order to actually apply this to a physical system, we had to add in some 2D physics into our 1D model. And so that brings us to what I like to call the 1D plus model. So I've been talking about a uniform flux tube, but if there were spatial variation along this flux tube, there'd be this area of localized pressure anisotropy that would stream out with the velocity of the particles. So in order, this is going to isotropize, so this thermal streaming is going to isotropize the plasma a lot faster than just Coulomb collisions alone. And so if this dominates the Coulomb collisions, then we can get a lot more scattering and a lot more heating. Magnetic pumping will be a lot more effective in actuality. So in order to verify this, we started by running VPIC simulations just to illustrate the role that thermal streaming plays in isotropizing the plasma. And so then we ran a set of new VPIC simulations to define a new kind of effective scattering frequency that reflects the isotropization rate from thermal streaming. And then we plugged that right back into our 1D model and to get how much energization and how the distribution function would evolve using this thermal streaming isotropization mechanism. All right. So this is the spatial domain of the VPIC simulations that we ran. It's very similar to the other VPIC simulation that I showed you before, although you might notice it's a much more elongated domain. The current sheets only cover about 20% of the spatial domain, and they don't cover the entire width. So pressure anisotropy is going to be created locally and then stream out with the velocity of the particles. So we again ran the simulation for a number of different scattering frequencies. Here we have distribution function as a function of velocity. And here you'll notice that every single scattering frequency is energized at the same rate, including the nu equals 0 scattering frequency when there's no scattering at all. And so as we've seen kind of in that initial case, there shouldn't be any heating at all from magnetic pumping. So clearly there's something dominating the applied Coulomb collision frequency. To get a sense of what that is, we ran another set of VPIC simulations. So in these simulations, we did not include any sort of pumping current sheet. We just set up a spatially varying pressure anisotropy, the domain of which is shown here on the left, and we measure the rate at which it decayed, the isotropization rate. And so we found that the isotropization rate for the electrons and the ions went as the thermal speed over the size of this perturbation, which tracks with the effective collision rate of the speed of the particles over the size of the perturbation. So exactly what we'd expect from thermal streaming. So using this new collision frequency, we plugged it right back into the 1D model that we had developed. And we used solar wind relevant parameters to find out how much heating and what kind of power laws we would get from, these equations. And so you can see here we've got red line is the initial distribution, and these colored lines are the temporal evolution of the distribution function from the sun to the blue line is transit time to Earth with kind of pessimistic solar wind parameters. You'll notice that these these lines aren't evenly spaced. That's because we didn't assume a coherent wave. For every fluctuation, we randomly sampled a magnetic field amplitude and a frequency from solar wind relevant parameters. So every fluctuation is a different frequency and amplitude to kind of simulate what it's like in the solar wind, and also to emphasize that we don't need a coherent fluctuation for magnetic pumping. All we need is for the magnetic field to go up and for it to go down, and then we can have pumping. So we end up getting these really nice power law tails, several decades. You'll notice that there's a point at which the power law ends. And so that comes from the fact that now we have a scattering frequency that's dependent on the velocity. So as the velocity increases, we're going to get a larger and larger scattering frequency, and eventually we're going to go, eventually it's just particles are going to be moving too fast to be magnetically pumped. And so this power law is going to end. And so for the ions, it's not that much of a problem. So here we have it in velocity, but if you look at it in energy, for the electrons, this power law turnoff comes before we can even measure it in the solar wind. And so in order to explain the behavior of the electrons, we really needed some additional physics. And so this is where the 2D model comes in. And this is the new result. So I'm going to start off. So for this one, we didn't run VPIC simulations, but we did compare the predictions of our 2D model to some observations. So I'm going to talk, before I get into kind of the 2D model itself, I'm going to talk about the data that we use to compare to our analytic results. And so this data comes from MMS, or the Magnetospheric Multiscale mission, which consists of 4 spacecraft flying in a tetrahedral formation in Earth's magnetosphere. So you can see Earth here in the center. It's a magnetosphere surrounding it, the incoming solar wind to the left. As the solar wind hits the Earth's magnetic field, it forms the bow shock. The leftmost red ellipse is the orbit of MMS in phase 1 of the mission, where it was studying day-side magnetic reconnection. And then the rightmost red ellipse is phase 2 of the mission, where MMS currently is, and it's getting some really great results in magnetic reconnection in the Earth's magnetochannel. So,
Emily, before you move on, can you just go back a slide? I think there's a question about the previous plot.
Sure.
And you
sorry.
Yeah. No, I realize your focus here is on the power law at higher frequencies, but I guess I'm trying to, maybe this is just what's fed into it. I'm trying to understand what's happening at low frequencies. At some point, should there be a turnover at low frequencies, or?
There's no frequency. So,
oh, at velocities, sorry, yeah.
Sorry.
Yeah.
Your question, why is there this question?
Well, why does it remain constant going to, it seems, arbitrarily low velocities?
Why is there no change over here?
Yeah, why doesn't it eventually drop? Is there never a deficit? I guess, yeah, this is not, yeah, I guess I'm trying to think if there's any region of this is like a Maxwellian. I guess it is.
So the red is the Maxwellian.
It is, okay, yeah.
And then
Okay, yeah, just looking at it in log space, sorry.
Yeah, so you end up in the transition from the Maxwellian to kind of this power law, you end up getting the shape. The low velocities are, you aren't really, so because it's a velocity.
Yeah, no, sorry, I was, yeah, just misinterpreting. But I think there's another question that's maybe a bit more informed from Dimitrios.
Go ahead, Dimitrios.
I'm not sure about informed, but question nevertheless. So you described what I would call maybe 2 different mechanisms or 2 different regimes of acceleration, right? One where the rate is proportional to the effective velocity or to the velocity, and the other where it isn't, but the actual energization is proportional to the velocity. Is that similar to like first and second order Fermi acceleration?
What do you mean by, so in both of these, you get the same, sorry, I was not clear. In both of these, you end up getting the same heating. So if you were to do kind of the 1D approximation, you'd get this velocity diffusion equation where the diffusion coefficient, you get delta V proportional to V. This is 100% Fermi acceleration. The only difference between this 1D model and the 1D plus model is how we calculate this scattering frequency. So you end up getting the same heating rate, essentially. But what I was talking about with the velocity is that because this V is now velocity dependent, as you get to higher and higher velocities, your effective collision operator gets higher and higher, and eventually you're in this regime where you're not really getting that much heating for the given collision frequency.
Yeah, no, I understand that. I guess what I was saying that in one case, D is independent velocity or it's just proportional to V squared. And in the other case, you have an extra velocity term because your effective collision frequency is velocity dependent, right?
Yeah.
And so that's why I was asking, there's, 2 types of Fermi accelerations, first and second.
So they're both order Fermi acceleration.
They're both second order.
For the, there's a velocity cutoff for the acceleration in the 1D plus model.
Okay, thank you.
Okay, yeah, sorry. So we 2D model, we're using MMS spacecraft. So the spacecraft are in the Earth's magnetosphere. And so the science mission of MMS is to resolve the microphysics of magnetic reconnection, and determine the kinetic processes that are responsible for collisionless magnetic reconnection. So previous missions required the spacecraft to do a full rotation in order to get a full 3D velocity distribution function. And since the spacecraft manually passed through a reconnection site for a fraction of a second, you really needed something much faster to resolve the kinetic physics. So here we have one of the MMS spacecraft with the diagnostics that measure the distribution function highlighted in red. DES are the electron diagnostics, DIS are the ion. And so each sensor is made of 2 spectrometers, and altogether the sensors can observe the entire sky and combine to produce a 3D distribution function every 30 milliseconds. So this incredible detail in velocity space distributions make MMS ideal not just for investigating magnetic reconnection, but also kinetic processes in general, including magnetic pumping. All right. So while the MMS spacecraft are supposed to stay within the Earth's magnetosphere, the solar wind dispersi, and occasionally will push back the Earth's bow shock, and the MMS spacecraft will cross the bow shock into the solar wind. And so it turns out that prior to the Earth's bow shock, there are these strong compressional magnetic fluctuations that form an ideal naturally occurring laboratory for magnetic pumping. So I have a plot of some of these fluctuations here on the right. So I've got magnetic field, density, observed temperature, and then the ratio of the observed temperature, the temperature you'd expect from compressional heating alone. So you can see from these like strong compressional magnetic fluctuations, we'd expect a lot of compressional heating. But there's, if we look at the observed temperature compared to the temperature we'd expect from compressional heating alone, there's a lot of energy that is unaccounted for. So you can see this in a little bit more detail in this plot down here. So here we have the pitch angle distribution function, or the pitch angle average distribution function as a function of energy for the, as we go across the bow shock. So on the left, sorry, we have the incoming solar wind. On the right, we have the Earth's bow shock. And so we'll look kind of as it goes towards the bow shock, how the distribution function evolves from yellow to the blue. And so this green dashed line is the amount of heating you'd expect from compressional heating alone of the yellow distribution function at the point denoted by this blue line here. So we can see a couple of things from this plot here. Number one is there's a lot more heating than can be expected, explained by compressional heating alone. Number two is that we get this energy transfer from lower to higher energy particles as we'd expect from a frame heating process, such as magnetic pumping. So a quick note, this blue dashed line right here is the energy at which our 1D model would have cut off for electrons. So it's far below even the point that we can measure it. All right, so we can look at these fluctuations in a little bit more detail. Here we've got magnetic fields, and looking over the course of a fluctuation, we can see the distribution functions. Here I have them plotted V parallel, V perp, where these red dashed lines are the trap passing boundaries. And so we can see there's a lot of trap passing physics happening in this area. And so this is a really great location to observe this 2D magnetic pumping, which involves these trapped and passing particles. All right, so that was where the data came from, but let's talk a little bit about the 2D magnetic pumping model. So the physical mechanism is the same as in the 1D pumping model. The main difference is that with Jean's theorem, we can recast the distribution function in terms of its adiabatic invariance, mu and j. And for this 2D setup, u and j are naturally going to take into account these trapped and passing orbits. And so we can use this new formalism to recast the distribution function, or we can use this new formalism to plot the distribution function kind of along this perturbed flux tube. And so we can take account not just the unperturbed orbits, but the perturbed orbits as well, and get the distribution functions shown here below. Again, we have V parallel, V perp. These red dashed lines are the trap passing boundaries. And so we can see that if we looked at the trapped population, as the magnetic field decreases, we get this cooling in the perpendicular direction, as we saw kind of on that initial slide. Additionally, you'll notice there's this heating along the trapped passing boundaries. So that is because of the just barely trapped particles that spend a long time at these inflection points. And so the energizing term, the mu dBdt, is very large and positive. And so we get a lot of heating along these trapped passing boundaries from these barely trapped particles. So we can, given how the distribution function evolves, with this 2D pumping model, we can compare to MMS observations. So here at the top, we have MMS observations, and then the results of the just 2D analytic model, no scattering, down below, for a fluctuation of commensurate size. So you can see the anisotropic features agree pretty well. There's some softening in the MMS observations. That's likely due to either incomplete confinement in a flux tube or some sort of pitch angle scattering. But we can use these to estimate the amount of scattering that is present in these MMS observations. So the way we do that is that we take one of our model distributions and then we apply progressively more and more pitch angle scattering until it matches well with the MMS observations. So here I have an example on the right for a scattering operator of 0.75. We can see that there's a lot better match between the model distributions and the MMS distributions. So I would like to just quickly note that these aren't just, I've been showing you the same fluctuation, but these are present kind of throughout this bow-shell crossing. So here we have this theoretical distribution near the maxima, this theoretical distribution near the minima, and maxima and minima across this entire bow-shell crossing. So the maxima are in the colored boxes, and the minima are the associated dashed lines in the adjacent boxes to the right. So you can see throughout this bow-shell crossing, we get this good agreement between the anisotropy predicted from our model and the MMS observations. All right. So now we have this estimate for the amount of scattering. We know how the distribution function is going to evolve. So it's pretty straightforward to find numerically how the distribution function is going to evolve in time from magnetic pumping and the amount of heating that we would get. So we can see this plot on the right of the amount of heating per fluctuation as a function of scattering frequency. Again, just like in the 1D model, if there's no scattering, there's no heating, there's an infinite amount of scattering, there's an infinite amount of heating, and we get, in between, there's the most efficient scattering frequency from magnetic pumping. All right, so this is great. We can get how the distribution function evolves. We can get how much energy, but it'd be really great to find an analytic model that would be able to get us more insight into what's happening physically, like we did in the 1D plus model. So it turns out with the 2D physics, the equation here is not quite as analytically tractable. And so we weren't able to solve it with the Lorentz scattering operator, but we were able to solve it by approximating the Lorentz scattering operator with the Crook operator. And so you can see the dashed line is the Crook operator approximation. The solid line is the Lorentz scattering operator from the one before. And there's good agreement between the two. So using this Crook scattering operator, we can find an analytic form for what this equation looks like. And so the result is down here below. I know it's very messy. The key point is this velocity diffusion equation here for the evolution of the background distribution function. So we get this velocity diffusion equation. The diffusion coefficient is proportional to v squared. And so that means we're going to get these power law tails. We're going to get this Fermi process. We're going to get that delta v proportional to v squared. And so we can see when we plot this analytic model on top, there's good agreement between the Lorentz, Crook, and analytic. And so now we have this beautiful closed form solution that shows us that we should be getting these power law tails that we do see. All right. So stepping back for a minute and going back to the Lorentz collision operator, because we have how the distribution function evolves and the estimate for the scatter frequency, we can compare what our model would, the heating we'd expect from our model for these solar wind relevant parameters, the heating we'd expect from MMS. So here we can see the heating we'd expect from pumping, and we add to that the heating we'd expect from compressional, because we are, as we go into the shock, getting more and more compressional heating, and we can combine those to get the heating we'd expect from our model for this bow shock crossing that I've been talking about. And we can compare that to the MMS observations from the same bow shock crossing. So you can see a couple of things. There's very similar amounts of energization. We get this energy transfer from these lower to these higher energy particles. There are some small differences at these lower energies. So that's likely due to the effects of the electric field. So this model neglects that. But I know Li-Jian Chen at NASA has a really nice model for how electric fields energize particles. But overall, we get good agreement between the model and the MMS observations, and we're very excited for this result. So while I've shown you this for just this one space physics application, we think this should be applicable to a number of astrophysical systems, really wherever there's compressional magnetic fluctuations. So we're excited to explore this in other astrophysical contexts. So thank you for your attention. Are there any questions?
I'll do the, I'll clap for everybody. People want to do their Zoom claps. Thank you, Emily, for that very interesting talk. I think we are a small enough group here that if people want to just raise a blue hand on the Zoom chat window, I can call on anybody who has a question. Give people a minute. Actually, can you go back to the slide with your agreement between the MMS and the your model? So I'm sorry, did you say this before? What sets the pivot point? Yeah.
Yeah, it is the power law that you get, essentially, and the initial condition. So
is there anything physical about that energy? Or is it just sort of where the power law matches on to the distribution?
There are important, the final power law number is something, the initial condition and the final power law are both, important. But the pivot point is mostly just like the point at which they cross. And so it's a reflection of those two physical parameters.
Okay. I see Andrew has his hand up.
Yeah, hi. Yeah, thanks for the talk. It's interesting to see some of these techniques that are somewhat similar to other areas, although a lot more advanced than what I do. In understanding the, I think it was the heating rate you were calculating, the script G, right? You were explaining that, and you did it obviously a bunch of different ways, but you've already non-dimensionalized that frequency, but I was just trying to understand again, you explained, right, what is it that optimizes that frequency?
What sets the most efficient frequency?
Yeah, is there a simple way of understanding what, so time scales that are equivalent, or, yeah.
So it is, it's probably most easy to see in the 1D. It is not the most easy thing to see from a, just getting it outside of, sorry, actually this guy is, so the 6 nu over omega is the most efficient for the 1D scattering frequency. And so it, essentially this 6 comes from the anisotropy. So
yeah, maybe it would help, maybe remind me what the nu and omega are, since obviously those are the key.
Yeah, absolutely. Yeah. So nu is the scattering frequency, and omega is the frequency of the applied fluctuation. So for the 1D model, it is a constant 6 nu over omega, this green line. So it's essentially, this 6 comes from the anisotropy, comes from this, this P2. So when you apply the Legendre polynomial, the Legendre collision operator, you get this, it ends up being this nice closed form for the the Legendre, when you apply the Lorentz collision operator, it's a nice closed form for the Legendre polynomials. And so you get this like n plus 1. And so I guess the most physical way of thinking about it is that this too is the second order velocity terms. And so that's going to be this pressure anisotropy is going to be is equivalent to that 6. So essentially, the pressure anisotropy is setting the most efficient scattering frequency.
Okay.
And so how offset they are. I like to think of the pressure anisotropy as kind of being dragged. Like it's not exactly where it's supposed to be. And so it's that dragging, that offset that creates the work. It gets a little bit more complicated for the 2D because the Legendre polynomials aren't good eigenfunctions anymore of the distribution function the same way they were before. And so you can see you get this traveling. There's a little bit of, it's a magnetic field dependent peak. And so that is essentially because the magnetic field is going to be stretching it, stretching the distribution function, those like trap passing boundaries are going to be changing and the anisotropy is going to be changing as well. And so that's kind of, you see that shift in the 2D, but not the 1D. I don't know if that.
Yeah, no, definitely. Yeah, thanks.
All right, I don't see any other questions. If there's somebody who couldn't find a blue hand and has a question real quick, I'll just pause for a moment and you can interrupt me. All right, if there's no other questions and no other pressing announcements, let's kick off to the